Welcome to Empowered Learning. This video will be about the ratio and root test for absolute convergence of an infinite series. So specifically speaking, we have two relatively easy tests to implement whenever we're dealing with an infinite series to see whether that particular series absolutely converges or not. And so although we're going to talk strictly about the ratio and root test, I'm also going to introduce a checklist for us to go by so that whenever we are trying to evaluate a series to see whether that particular series converges or not, we kind of have a pecking order of knowing what to look at and when. But of course, the ratio and root test are a part of that. So first, I'm going to introduce what the ratio and root test are. We'll look at an example or two, and then I will introduce this list or this checklist to see whenever we're looking at a particular series, what is the most efficient way to figure out whether that particular series will converge or not, and what test we need to consider based upon the characteristics of our series. So for our ratio test, we see here that if we have some series and this series looks like what you see here, then what we want to consider is what the nth term of the sequence that makes up that series is, which is a sub n, as well as the n plus 1th term, a sub n plus 1, and we want to do the quotient of a sub n plus 1 divided by a sub n, take the absolute value of that, and then evaluate the limit of that result. And so here, if we get some real value that is less than 1, then we know that the series that we were considering is going to be absolutely convergent, which by default means that the original series that we were looking at is also convergent, okay? And remember here that absolute convergence just means that we know that this corresponding series, meaning the series where all our sequence that's made up of it is stripped of all of its negative terms, okay? And what I mean by stripped by is negative terms. Let's say if we have a negative 2/3 in for a term, we strip out the negative and the positive part, or the 2/3, remains for that particular term, okay? So if we know that the real number value that we get is less than 1, then we know it definitely converges absolutely. If we have a situation where the limit goes to infinity, or if the limit is greater than 1, then we know that this corresponding series is going to be divergent, basically. And if it is limit is equal to 1, then it's inconclusive, meaning that we're essentially just going to have to find another way to be able to show whether that particular series converges or not. And that's part of the reason why we want to go through that checklist that I mentioned earlier, okay? So again, main thing is we want to evaluate the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And of course, if it's less than 1, here, real number, less than 1, absolutely converges. If it is infinity or greater than 1, then it's going to diverge. And of course, if this limit here equals 1, then it's inconclusive. Now, we have this test here, but we need to kind of dig a little deeper just to understand, well, what is this really trying to communicate to us, okay? So if we think about it, if we take the limit of the quotient of two functions, essentially what it is that we're trying to do is figure out which function grows faster, okay? And so what we're essentially doing here for this ratio test is we are comparing what a sub n and a sub n plus 1 would look like to each other. And so whenever we have a situation here where our limit of the a sub n plus 1 divided by a sub n is less than 1, what we are essentially saying is that whatever this value for a sub n is going to be at least slightly larger than the a sub n plus 1. Putting that another way, we're showing that a sub n, as the values of n get higher and higher, are going to be decreasing. Okay, so that's essentially what we're saying there. Now, when we come here and we say that the limit of absolute value of a sub n plus 1 divided by a sub n goes to infinity or greater than 1, what we're saying is that the subsequent terms of the sequence a sub n, as n gets larger, is actually producing bigger numbers. Okay, so that means a sub n is smaller than a sub n plus 1, which means that as n increases, the a sub n plus 1s are going to get bigger and bigger and bigger. So it's kind of like having something that goes like this: 1, 1.2, 1.3, 1.4, where this is your a sub n plus 1, this is your a sub n. Okay, so it just keeps on getting larger. But here in this situation, this is kind of like having 1, 0.9, 0.8, 0.7, so on and so forth, where here the a sub n plus 1 is 0.8, where the a sub n is 0.9. We see that the a sub n plus 1 is a smaller value than the a sub n for this particular value here. Okay, so that is essentially what's going on. Whenever the limit here is equal to 1, what we're saying is that these two functions here are decreasing at pretty much the same rate, or increasing at the same rate. So there's not much difference in between these two terms as far as how fast they increase or decrease. Okay, so in that sense, we can't really determine, because this a sub n plus 1 and this a sub n are too closely related to each other to be able to know, hey, is the a sub n going to be bigger or smaller than the a sub n plus 1 as we use more values of n and list those numbers out. So that is what essentially the ratio test is trying to do. So now let's talk about the root test. And so what the root test is, it is essentially the same kind of flavor as the ratio test, but we use this test whenever we have sequences that are defined to where we have some sequence and there is like raised to the n power or raised to the 2n power or something like that in it. So we use the root test to help us deal with those type situations. And so again, same thing. In this sense, we have the limit as n approaches infinity of the nth root of the absolute value of the sequence that makes up this particular series here. So of course, this is the series that we're considering. Do absolute value of what a sub n is, take the nth root of it, and that'll usually get rid of the power of n in the exponent. And then of course, we just take the limit of that. And of course, if we see that that limit ends up being less than 1, then it absolutely converges. If it is infinity or some real number value greater than 1, then it just means that the series is going to be divergent. And of course, if it's equal to 1, then we're going to have to find some other test to prove convergence or divergence. And usually in this case, again, whenever we talk about this criterion number 1 and criterion number 2, if our root test fails this and goes to this particular situation, then more than likely what that means is that the series that we have, if it is going to be convergent, it will be conditionally convergent. Okay, and so that's the same thing for the ratio test. If it doesn't meet either criterion number 1 or criterion number 2, then if we need another test to be able to do it, if it is convergent, then more than likely it's going to be conditionally convergent because of that. So for the examples that we're going to look at here, the directions are pretty much the same. We want to determine whether the following series that we're going to look at here are absolutely convergent, conditionally convergent, or divergent. We first want to consider the ratio or root test, and if needed, we'll consider other tests. All right, so if we look at this first example here, and the first few examples I'm going to have already worked out, so I'm going to talk through these relatively quickly because everything is worked out. Of course, you can pause the video at any time if you need to look at any particular steps, but I just want to run through a few examples just to kind of give you the flow of how these problems go. And then after that, then we'll actually start to work some out from scratch. So for this first example here, we're considering this series, and of course what's on the inside here we're going to consider to be our a sub n, and so we let a sub n just be what was originally given, a sub n plus 1. Everywhere where we see n, we just add n plus 1, and then we just figure out what the absolute value of a sub n plus 1 divided by a sub n is, and you see we've actually wrote that, and then at this point it's just a matter of algebraic manipulation to get it to what it's supposed to look like. So once we're there, then we just take the limit of this result as n approaches infinity. And of course here, in doing that, it's pretty simple. We just let n be infinity here, and we know that 1 divided by infinity in terms of limits goes to 0. So we just got 1 plus 0, which is 1. So all this is 1, and 1 times 2/3 is 2/3. And so since 2/3 is less than 1, then we know that the series that we were originally dealing with is absolutely convergent, or converges absolutely. Therefore, it's going to converge regularly. Okay. And again, this is a situation where we don't have like an alternating series type thing going on, but we see that that particular series is going to converge, absolutely as well. Okay. As well as regular. So for our next example, again, we have a series that we're dealing with, and this one has an alternating series component in it, or alternating term component in it. So we let the a sub n just be what the actual sequence that makes up this series is. The a sub n plus 1, everywhere where we see n here, here, and here, we just let it be n plus 1, and then we figure out what this is going to look like. Okay, so we take what the a sub n plus 1 is, which is this, divided by the a sub n, and of course here, this is the a sub n plus 1 part here. And when I divide it by a sub n, since I have a fraction being a fraction here, being divided by another fraction. Oh, sorry. I think I circled the wrong thing here. Let me go back. Yep. So let's try that again here. So this is your a sub n plus 1. This is your a sub n. And notice that I have essentially a fraction being divided by another fraction. Okay. So I would have to do this fraction multiplied times the reciprocal of this one. And so that's what you see here. So here is the original a sub n plus 1. And this is actually going to be your 1 over a sub n. Okay. So that's what I was trying to say here, but I think I got a little ahead of myself. So once you do all this, and it's just a matter of reducing everything and collecting terms to get it into something that we can work with. And so here we see that what we end up having is this -1, or basically a -1.1 times 1 over 1 plus 1 over n, all that raised to 4. Okay. And of course, if we take the limit of that, we'll see that once we start working with our limit laws and all that and do the absolute value, that we eventually get to the point to where we evaluate this limit and it ends up being 1.1. And since 1.1 is larger than 1, then we know that the series that we dealt with is going to diverge. So for the next example, again, we have our series. We see that it's another alternating series one. So here, whatever we were given, inside of here, that's going to be the sequence that formulates this series. And everywhere where we see n, if we replace it with n plus 1, then we'll get what a sub n plus 1 is. We take the a sub n plus 1 divided by a sub n, which is the same as saying we take the a sub n plus 1 here, and we are going to multiply it times 1 over a sub n, okay, or the reciprocal of whatever this is. And again, we do all that and try to manipulate algebraically to reduce as much as we can and rewrite as much as we can to get this into a form to where it's going to be easy for me to evaluate the limit of. Okay. So once I figure out what a sub n plus 1 divided by a sub n is, then I take the limit of the absolute value of that. And of course, here you see, I know this doesn't look like the prettiest thing here, but it is written in a form that allows us to be able to evaluate the limit relatively easy. Of course, once we're in this form here, then, and we got all the alternating signs, portions of factors of it stripped out, then we know that the limit of the product of two functions is just the limit of each one being multiplied together. And so that's why I'm doing limit of 1 plus 1 over n. And then, of course, we'll take the limit of all this info too. And via our limit laws, we know that we can slide the limit operator under the square root sign. Okay. And so that's why we have this looking this way. So once we're at this point, we can essentially, due to a lot of limit laws, just plug in infinity for n, and we know that 1 over infinity in terms of limits goes to 0. And so once we do all that, we see that we end up with 1 here. So what this is telling us is that our original alternating series that we have here, it's not going to be absolutely convergent, okay? However, this particular series may be conditionally convergent if it meets the properties of the alternating series test, okay? And so here we see that since the limit is 1, it's inconclusive. So we're going to try the alternating series test because of the fact that it is an alternating series, okay? And so I'm going to finish this example, and then I'm going to show you that checklist, and you'll see why we're sort of considering the alternating series test at this point. So we're going to use the alternating series test since the ratio test didn't work for us here. All right, so the two things that we need to look for with the alternating series test is that if we look at the non-negative version of our sequence values, we need to know that the subsequent value in the sequence as we plug in higher and higher values of n is going to be a number that's smaller than the current, okay? So we need basically a sub n, the absolute value of that, to be bigger than a sub n plus 1, absolute value of that. And here we also need to make sure that whatever the absolute value of a sub n is, which another way of saying that is the limit of b sub n, we need to make sure that that definitely goes to 0. Okay. So the first thing that we'll do is verify that the absolute value of a sub n is going to be larger than the absolute value of a sub n plus 1 for all values of n greater than some natural number here. So essentially what we're trying to say is that we want to see that a sub n ultimately decreases if we strip out the alternating sign factors of it. So if we look here, as I list these values here, notice that what happens at first is that we have this value, then it goes up, and then it goes back down, 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 and it just keeps on going down So what we know is that beyond, let's say in this case, beyond big N is equal to 2, we know that absolute value of a sub n plus 1 is going to be smaller than absolute value of a sub n. Okay? So what that tells us here is that current term is going to be bigger than our subsequent term, or the next term after that. Okay. Also, if we go ahead and look at what the absolute value of a sub n is, which will be just this portion is your absolute value of a sub n, then we see here that after we do some algebraic manipulation and such, that the limit of that particular sequence will go to 0. And that is the second condition that is been met. So we've met the first condition of the terms of the absolute value of the original sequence that made up our series is ultimately decreasing. The other thing is that the limit of the absolute value of our sequence here goes to 0 as it approaches infinity. So because of that, we know that our particular series is not going to be absolutely convergent, but it will be conditionally convergent. Okay. All right. So now that we've sort of seen what happens whenever we have an inconclusive test, I'm now going to switch over and we're going to talk about this checklist to see whenever we're dealing with series, how we can have some kind of order into figuring out whether a series is convergent or not. All right, so what I have here is a summary of tests that we use to be able to figure out whether a series converges or diverges. I know that the textbook that I currently teach out of actually has this particular thing in it, so that's where that actually comes from. I think it's a good list here. It's nice, succinct, kind of gets to the point. So, of course, the very first thing is that if we want to test for convergence, it's nice to know if what it is that we're dealing with is divergent to begin with, okay? Because we don't want to waste a whole lot of time if we don't have to. So the nth term test for divergence just basically says that unless the sequence that we're dealing with, if the limit of that unless it approaches 0 as n approaches infinity here, then our series is going to diverge, okay? So put that another way, if we know that the limit as n approaches infinity of a sub n is equal to 0, then there is a possibility that our corresponding series will converge or it will diverge, okay? So this is inconclusive. Okay. So if we have a situation where this is equal to 0 or it's plus or minus infinity, we know it automatically diverges and we're done. Okay. So we use the nth term test for divergence first. And to me, that's should be the first thing that you always use, unless you recognize something like, hey, it's a geometric series that you're looking at, or a variation of a theme of that, or some kind of P series, okay? And that also includes the harmonic series. Remember that geometric series converge as long as the common ratio R here is in between -1 and 1. Our P series converges only when our value of P is greater than 1, okay? And notice that the harmonic series is exactly when P is equal to 1. So the harmonic series is just P series when P is 1, and of course at divergence, okay? Now, if we know that our series here does not pass the nth term test for divergence here, basically saying we have this situation and it's going to be inconclusive, then we know that if it's not a geometric series or some type of P series, then we want to say, hey, is it series with non-negative terms in it? Okay. So if it is, then of course we can try the integral test, ratio test, root test. And the order in which you probably want to do this is you probably want to do the ratio and root test first, since it's relatively the easiest to do. And then after that, you probably want to do the comparison test or limit comparison test second. And then lastly, you want to do the integral test, okay, in that step. So if you have series with non-negative terms, your integral test is going to be the last thing that you want to do because that requires the most work, okay? So if your series has some negative terms in it, and you'll know, and you'll definitely know that if you have something like a -1 raised to the n, or n-1, or n+1 in it, you definitely know you have some negative terms there. So then what you want to do in those instances is you want to figure out, does the series with the absolute value of a sub n converge? In other words, you're trying to figure out if it's absolutely convergent or not. So if what you're looking, so basically if you strip out all the negatives out of all the terms that are originally negative in your series a sub n, and you look at what you have left and you're like, hey, I know that particular series converges, then you're going to know that it's absolutely convergent, okay? And again, a way to be able to do that is to do ratio or root test, okay? So let's say you try out 1, you try out 2, you try out 3, doesn't work, and you know that some of your terms in the series is negative. You'll skip 4 and you'll come straight to 5. And you'll say, all right, well, can I test for absolute convergence? Well, yeah, you can do that by using the ratio or root test, okay? If it's not absolutely convergent, then of course you want to use some of these other tests I've mentioned, like the comparison test or limit comparison test or the integral test, okay? Now, if you have a situation where you specifically have this factor of -1 raised to some power of n here, then of course you want to skip and go all the way down here to the alternating series test to do it, okay? And of course, we've talked about the alternating series test before, but basically we just need to see for this a sub n here, if the absolute value of that, which is equal to b sub n, if these terms ultimately decrease and these terms approach 0 as n approaches infinity. So if we know it passes that, then we know that our series will conditionally converge by the alternating series test. Otherwise, it's going to diverge. So for our next example, we want to see what happens whenever we have a series where our underlying sequence is something that's raised to the power of n. So here we do the same thing, but now we're going to be applying the root test instead of the ratio test. So we just say what is going to be the nth root of the absolute value of a sub n. So we just take all this business here, and we just take the absolute value of it, take the nth root, and you see that, of course, we do some fancy footwork. The nth root of all this raised to the n just gets rid of the radical sign altogether. And then, of course, from here, again, I'm just, I don't have to rewrite it like this, but I'm doing it so that it's very easy for me to take the limit of it once I'm done. Once we're here, then, of course, you see it's very easy for me to plug in infinity for n here and know that 1 divided by infinity squared is just going to go to 0. And, of course, since 1/2 is less than 1, which is my final answer, I know that this particular series that I'm dealing with here is absolutely convergent, which means that it's going to be convergent, okay? All right, so for this next example here, this one's going to be a little bit more involved. So we have a situation here where this is our series where we're doing a summation of 1 plus 1 over n, all that in parentheses raised to the n squared. And we see here that our a sub n, we're just going to let it be whatever the corresponding sequence is that makes up this series. If we do the nth root of that, then the absolute value of it, then what we end up with is just 1 plus 1 over n raised to the n at the end of the day here, okay? And so we are asked to take the limit of 1 plus 1 over n, all that raised to the n as n approaches infinity. And we see that we end up with a 1 raised to the infinity case. And contrary to popular belief, that is not just 1. That is an indeterminate form, an indeterminate power to be exact. So whenever we have that situation here, what we do is, instead of trying to figure out what is going to be the limit of this as n approaches infinity directly, what we do is just basically let this function here be y, and we find out what is going to be the limit of natural log of y, work on that, and then we use our limit laws as far as limits of composition functions to be able to figure out what the limit of y actually is, okay? So here we have natural log of y. So basically natural log of this side equals natural log of that side of that equation. And per our logarithm properties, we can take this in, pull it out in front. And once we get here, we automatically know from first year calculus that if I was to take the limit of this term here, that what I would essentially end up getting is an indeterminate product here of infinity times 0. And of course, whenever we get infinity times 0, indeterminate form, that tells us that one of the two functions that we're multiplying, we're going to have to rewrite as 1 over the reciprocal of itself. And since n is the easiest to rewrite as 1 over the reciprocal of itself, like here, 1 divided by reciprocal, which is just 1 over that as well, then this automatically turns into either an infinity over infinity over a 0 over 0 case where we can use L'Hopital's rule. Okay. So from there, we say, what is the limit of natural log of y? It's same as evaluating what is the limit of natural log of 1 plus 1 over n divided by the 1 over n. We automatically know that we have to use L'Hopital's rule. So we take derivative of numerator and denominator separately. From here, we simplify and we just get the limit of 1 over 1 plus 1 over n. And then, of course, from there, this ends up being 1 as a result. And so please do not get confused. This 1 goes with the limit of natural log of y, not of y. Okay. And so to find out the limit of y, we use our logarithm properties to rewrite y as e raised to the natural log of y. And then our logarithm properties allow us to take this limit operator here and slide it to the inside function. So that's why you see that. And of course, the limit of natural log of y as n approaches infinity is 1. So all of this is 1. And of course, e to the 1 is e. And if you remember, e is approximately equal to 2.71. So it is definitely greater than 1. So we know in this case, by the root test, that it's going to diverge. Because remember, if our limit is less than 1, then it absolutely converges. And if L is greater than 1, or infinity, then the result is that it diverges. Okay. And then, of course, if we have anything else, which is the only other thing else you can have is when L is equal to 1, it's inconclusive at that point. Okay. And for some reason, I can't write an I and a V here. I'm trying really hard. All right, so let's move on. All right, so the next thing that we're going to do is work several examples where they're not already worked out. And since I have a bunch of these, I'm going to make another video. So this will be a part 2 of this series on ratio and root tests to go over those examples so that we won't have to look at all of them in this one video here. So catch me in that next video where we go over some more examples of doing ratio and root test, and hope that all these examples help. Take care.